Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. Now, this should be a shorter video where I'm just going to talk about a simple quirk, fact regarding how springs function and how, yes, I was never aware of it because nobody explains any of this physics as, an obligation to recognize that it's all physical processes and you have to account for what the physical processes are actually doing. And physicists don't bother with any of that. So frankly, and so I'll give a quick, hopefully, explanation. So I'll be back shortly. All right, back. All right, so spring, simple enough device, and you have this understanding that yes, you're going to lose something from a spring because it's going to move. Okay, it's going to stress the material, so it's going to get a little bit hot. Okay, so you're going to lose some energy from just the fact that the metal is going to be stressed and it's going to produce a little bit of heat. You can produce more heat by really working the spring. You can break it and all that kind of stuff. So it's going to dissipate some of its energy. The energy you're going to use to compress it is going to be lost. But there's this idea that it's relatively efficient in terms of collecting, energy. All right, and now we're stuck with this word energy. Is energy momentum or is energy kinetic energy? Okay, and I would argue that all it can collect is momentum. That in any interaction between things, the only thing that ever is exchanged between forces and objects between objects and objects is momentum. Kinetic energy is just a fable. But anyway, regardless of that understanding, so you can understand that compressing a spring, it looks pretty efficient. You put energy in, the spring absorbs the energy, and it's stuck with a certain compression. That is, when it's fully taken everything and stopped the other object, meaning it's absorbed all of its energy, and the object stops, that means it's done. It's finished giving away what it had. And the spring now has that energy potential, and it's sort of a real potential energy instead of the fake, gravity potential and all the other circumstantial potentials. This is real potential in the sense that you've actually taken, on a molecular level, you've created a bunch of electron pressure inside the object, and that pressure exists and is being contained, and you have to contain it with a constant force of some kind. So you have to use some kind of rigid body that cycles the force, or you have to do something to hold the pressure in the spring. The spring doesn't hold it by itself, so you have to mechanically hold the pressure. So I could just take a steel thing, a U-shaped thing, and put the spring inside of there, and that'll hold the pressure. But you can understand, you can think about it and say, well, the pressure must be stressing it, right? Because if I made the steel out of cardboard instead, right? If I made this U out of cardboard, the cardboard would slowly give way. And I could take cardboard and then I could put water in it and it could watch it degrade in terms of its capacity to provide that resistive force. So it's obviously providing a resistive force, and that force has to be traveling through the whatever you're made that U out of. All right, so the real point of this video is about when you release this potential. So you've absorbed the potential. Let's say you've conserved 95% of its power. The problem is now releasing, because releasing is going to be different than absorbing. Absorbing, there's a clear, the energy of the thing going in, is going clearly down as the potential of the spring is going clearly up, and there doesn't seem to be much that you're losing. But on expanding, you can understand the spring is going to expand at an accelerated rate, at a velocity. So it's going to actually move with a velocity, and the lighter the object, the higher that velocity. So a light object is going to move with a fast velocity because you're going to give it its momentum, the momentum you've stored. And a heavy object will move at a very slow velocity. So if I have something 10 times heavier, it's going to move 10 times slower away from the spring. And so when the object actually leaves the spring, that is, it's gotten enough energy to be going faster than the spring is going. So the spring is pushing, pushing, pushing. It gets up to a speed where the spring doesn't have enough energy, okay, mass and velocity, to keep up with what it's pushing. So the spring doesn't just push something and then stop moving. The spring continues, okay, but it continues slower than the object's moving away. So the object moves away a little bit faster than the spring's moving, but the spring has still got energy in it. It still can push something. If it were something lighter to push, it'd be able to push it. But there's nothing else left to push, so the spring expands with whatever energy it has left. It expands and contracts and expands and it contracts. So you can understand that a light object, the spring will be moving at a very high, so it's the same spring. The spring will be moving at a very high velocity when the high velocity object, the light object, leaves at a high velocity. So now the spring's moving at, say, 50 miles an hour when I have a light object, okay? And now it's going to oscillate with that 50 mile an hour velocity, okay? So it's obviously going to be a lot more momentum is still left in the spring as it's oscillating. And if I push the heavier object, well, when the object leaves, it's only going to be 10 miles an hour. So now the oscillation is going to be much smaller because much less energy is still stuck in the spring because it's only going 10 miles an hour now. Get it? So clearly pushing light objects is really inefficient at getting your energy back, and pushing heavy objects is more efficient. And so you could imagine that if you took a little tiny piece of styrofoam and pushed it with a spring, put it on the end of a spring, well, it's going to be going the same speed as the spring essentially, pretty easily. It's going to get up to the same speed. And there'll be that point where it's going to be going the maximum speed, and the maximum speed will be the speed of the spring itself. So almost 90% of the energy will be left in the spring, and you'll only get 10% into the styrofoam. So shooting something very light, you're not going to be able to transfer the momentum. But the heavier you're trying to push something, the more that you're going to be able to get into the object, short of it being too heavy to push, which is the same as the brace holding the spring. So if it's too heavy to push, then the pressure doesn't go anywhere. If it can be pushed, the energy will go from the spring into the object quite efficiently. So it makes a huge difference. So they do a lot of experiments, where they claim an elastic principle, that is, that should happen when hard objects hit hard objects, like a Newton's cradle. And they change the experiment by essentially, so when they do a Newton's cradle, they don't bother putting springs, okay, on the balls, right? There's no springs, right? And it works quite efficiently. But when they're using a car, when they want to use a 10-mass car, let's say, and they're going to hit a 5-mass car, what they'll end up doing is sticking a spring in between. All right. Even though they're hard steel objects, even though they would elastically reflect, they make it a super elastic experiment. That is, they introduce this spring. And the point is that when you do an experiment, let's say where you're pushing two 10 masses away with the spring, there's going to be a lot more of this energy in this spring is going to go into the objects. And say if you're going to push 5 masses, okay, the spring is going to still be going a much higher speed when the masses leave. So the spring is going to keep a lot more of the energy. So in this experiment, you're going to get less total momentum going this way and this way than you had total momentum in this experiment, merely because the spring is going to hold more of the energy. So it's a really important fact, okay? It's a variable in experiments. You're not guaranteed that springs give their energy equally to all objects. It's really important to understand that when you're doing experiments with springs in them, that lighter objects will, in fact, absorb less momentum from the spring than a heavier object. That's the takeaway point. All right, so I'll keep it short and just say no physicist tells you that. There's no paper written somewhere about springs and how they don't perform very well as you vary the weight of the object you're pushing with the spring. And it's, when you think about it, it's just obvious. It's obvious the spring is pushing, it's increasing the acceleration of the object, the velocity, and there's some point where the spring is going the same velocity as the object, and then there's a point where the object's going a little tiny bit faster than the spring is moving, and now the spring is stuck with that energy. It can't get rid of it because there's nothing to push on. All right, so yeah, it really should be. For anyone high school literate, they should have understood the point. So we'll leave it there. Thank you very much, and such.